In Chapter 5, Continuous Random Variables, the most basic distribution we will study is the uniform distribution. We use the uniform distribution to model an experiment where the outcomes are numbers that are all equally likely to occur from some value A all the way up to some value B. Study this section to learn the most basic properties of a random variable x that's distributed uniformly from A to B. Example 8. Find the probability density function of a random variable x distributed uniformly from -2 to 13 and its cumulative distribution function. So we could find this using the properties above, but why does it work? Well, we know that the uniform distribution should be flat, okay, and it also has an area totaling 1 underneath it. Well, that would form a rectangle. We know that the length of this rectangle is 15 units. And for length times width to equal 1, that must mean that my width, or perhaps the height here, needs to equal 1 over 15. So my PDF becomes little f of x equals, we know it's going to be 0 when it's not, when it's greater than 13 and when it's less than -2. And it's going to be 15 when x is between the numbers -2 and 13. And we can also put equals there as well, but it's up to you. Everywhere else, or otherwise, f of x will equal 0. Here I typed up the PDF neatly. So by definition, the cumulative distribution function is the probability that x is going to be less than little x. Okay, and we can break this down into 3 different cases. How about when x is less than -2? Well, the area to the left of -2 is 0, and also for any value that's going to be less than it. So for instance, -3, the area to the left of it is still 0. And we also know that once we reach here, all the area to the left is 1. So when x is any value that's 13 or larger, the area to the left of it, or the probability that x will be 13 or smaller, is a sure thing. And from -2 all the way up to 13, the PDF will gently rise. There's not going to be any large increase. So we'll have x minus -2 all over 15, which will allow this to gradually rise. And so if we plug in -2 here, we'll see that this will become 0. And then when we plug in 13 here, we notice that the number we'll get is 1. So this starts off at 0, rises up to 1, which is what we are aiming for. Here is the graph of the cumulative distribution function. Here in UTRI 17, you should verify that the mean and standard deviation of this particular uniform distribution, using first the properties on page 102 above here, and then using the definition found on page 97. I left you some space here for you to write the definitions and then to compute them using your calculator. So pause here, go ahead with that, and then check back with my answers. The first part, using here this definition, the mean is going to be halfway between the starting and ending points, is pretty straightforward. We found that the mean should be 5.5. Now let's compare this to the definition found on page 97. Hopefully this will all equal 5.5. So we need to integrate from -infinity to infinity x times f of x. But we notice here that f of x will equal 0 everywhere other than from -2 to 13. So we can limit ourselves to this range. And f of x equals here now 1 over 15. Here on GeoGebra, we can find this. We're going to integrate this function, and it's x times my f of x value is 1 over 15 from -2 all the way up to 13. And we still get 5.5. The standard deviation from page 102, we can take the square root of the variance, which is the range squared divided by 12. Take the square root of that, all we're left with is the range divided by the square root of 12, which in this case would be 15 over the square root of 12, which is approximately 4.33. Now we'll compare that to the definition, which is we'll take the difference of the x value minus the mean squared times f of x, integrate from -infinity to infinity, or in this case just from -2 to 13, and then we'll square root the variance. Let's use GeoGebra. Here we integrate the function x minus mu, which was 5.5, squared times the f of x, which in this case is 1 over 15, starting from -2 all the way up to 13, and we get 18.75. Now we just need to take the square root of that, and we get 4.3. We've thus reviewed the definitions for mean and standard deviation, and also verified that the properties given above here will indeed give us the true mean variance or standard deviation that we learned from 5.1 Part C. You try 18. A plumber estimates that service calls are uniformly distributed between half an hour and 8 hours in length. Do the following on your own, then compare your answers with this media lesson. For instance, let x equal what? You try this, then check back. Hopefully you paused the video and wrote down your answer. Mine was that we are letting x equal the amount of time that a service call takes. And we're going to measure that in terms of hours. What is the distribution of x? I want you to try to answer this question, then check with this video link to see what is the correct answer. You try 19. Scientists are waiting for a monkey to fall asleep. The chance the monkey will fall asleep is constant from now until 17 hours and 30 minutes from now. Then we'll let x equal what? We're measuring x, which is the time before the monkey falls asleep, measured in hours. How is x distributed? Because the probability that it falls asleep from right now to 17.5 hours from now is the same or constant, this is uniformly distributed from 0 to 17.5. And you try 20, find the probability that the monkey will fall asleep within 7 hours, from between 3 and 10 hours, after 15 hours, and then at 2 hours, 3 minutes, and 41 seconds. Hopefully you found the same answers as I did. So the probability that the monkey fell asleep starting from 0 all the way up to 7 hours, well, that's around 40% of the entire time, or 7 over 17.5. Here, the probability that the monkey fell asleep between 3 hours all the way up until 10 hours So we have a duration of here 7 hours out of the total 17.5 hours that it could have fallen asleep. So that would still be 7 over 17.5. The probability that the monkey falls asleep after 15 hours, so we go to 15. So it looks like this has a total of 2.5 hours possible out of the total of 17.5. So here this would be 2.5 divided by 17.5. And finally, the probability that x equals this particular, that the monkey falls asleep at 2 hours, 3 minutes, and 41 seconds would equal 0. The probability of any particular outcome in a continuous random variable is always going to equal 0. In other words, the area of this line is 0 because it has no width. You try 21. Find the mean and standard deviation using the properties from the previous page. The mean is fairly straightforward for the uniform distribution. We take halfway between the starting and end values, and that will be my mean. And make sure to add the units of measurement. In this case, it'll be 8.75 hours. For this standard deviation, we take the range and divide it by the square root of 12, which in this case turns out to be around 5.05 hours. You try 22 and 23. Find the probability that x is less than the mean plus 2 standard deviations, and also the probability that x is less than the mean plus 3 standard deviations. If you recall, both of these values were used to help us find the upper cutoff value for unusual events or unusual outcomes. For you try 22, the probability that x is less than, this number turned out to be 18.9 hours. Well, that will be 1 because it can only go all the way up to 17.5. So if we were to go even farther than that, I don't even need to compute what this number will be because the probability of x being less than it will certainly still be 1. And it turns out that this number actually will be 23.9, I believe. This brings us to example 9. Which range rule should we then use for the uniform distribution? Well, it would seem that if all of my events would occur between the range of here mu minus, this brings us to example 9. What range rule should we then use for the uniform distribution? For bell-shaped or mound-shaped distributions, we were able to use the one that went from plus 2 sigma minus 2 sigma from the mean. And it looks like this would also be a good choice for the uniform distribution. So for all x values between mu minus 2 sigma up to mu plus 2 sigma, these would be usual, or the probability that we would that x would be between these two values should equal 1. Therefore, usual values should occur within this range. Outliers would be beyond them. So if c would be less than this value, then it would be a very low outlier. And if d is greater than this, then d is a high outlier. And most likely that would mean that this would be an error in measurement. You can skip part B if the difference between continuous and discrete random variables makes sense to you. This is just another comparison between the two. So we have an experiment. Andre goes scuba diving at various locations, and when he steps off of the plane, he wants to figure out how much time until low tide when he can go scuba diving at a certain site. We assume low tide occurs every 12 hours. This appears to be a uniform distribution. No particular time from when he gets off the plane to low tide seems to occur with more probability than any other time. Now, if Andre only looks at the hours until low tide, then this would be a discrete distribution from 0 to 11.